Something massive is stirring at the center of our galaxy. A black hole with the mass of 4 million suns sits there, silent right now, surrounded by clouds the size of 200 light years, rivers of gas, ancient explosion scars, and bubbles of radiation so enormous they cover half the sky. We could never see any of it with our naked eyes. The dust hides everything. But astronomers just cracked the curtain open, and what they found changes everything we thought we knew. A giant cloud nobody detected until last year. A particle trap running at energies that should be impossible. Evidence of a blast so powerful it reached another galaxy. If you enjoy what we cover here, subscribe and hit that like button. Now buckle in. We begin. There is a wall between us and the heart of our galaxy, and it is made of something you would never expect. Dust, gas, billions of years of cosmic debris stacked so thick that every single photon of visible light gets swallowed before it can reach us. If you pointed the most powerful optical telescope on Earth directly at the galactic center, you would see nothing. A dark smear. A void. The most violent, energetic, and active region in the entire Milky Way. Completely invisible to human eyes. And for most of human history, we had no idea what was hiding there. Think about what that means. Our galaxy has roughly 400 billion stars. Every single one of those stars, including our sun, orbits around a central point, a beating heart, and for centuries we could not see it at all. The center of the thing we live inside was a mystery wrapped in a wall we could not break through. The dust lanes responsible for this blackout are so dense that light would have to travel through the equivalent of thousands of miles of solid rock just to get past them. Visible light has no chance. It hits the first layer and stops, then the second, then the third. The wall just keeps going, stretching across thousands of light years of packed cosmic material, completely sealing off the core from view. Here is what makes this strange. We can look in almost any other direction and see galaxies hundreds of millions of light years away. We can spot ancient light from the very edge of the observable universe. But our own galaxy's center, roughly 26,000 light years away, sat completely hidden from us until we figured out how to look in a completely different way. And even then, what we found left astronomers stunned. The dust does not just block light. It absorbs it, heats up slightly from the energy, and then re-emits it in a form we cannot see without special instruments. So the center was not just dark, it was actively hiding from us, re-radiating every attempt we made to look at it into invisible wavelengths. Scientists in the 20th century began to suspect something enormous was lurking behind that wall. Stars near the outer galaxy moved in predictable, calm patterns. But the further inward astronomers looked, using early radio telescopes that could pierce through dust, the faster and more chaotic the motion became. Something was pulling everything with an enormous gravitational grip. Something with a mass so staggering it was almost impossible to calculate. The wall of dust was not just an inconvenience, it was a lid on the most powerful engine in the Milky Way. What finally broke through was not light at all. It was radio waves. Long, slow wavelengths that dust simply cannot stop. When astronomers first tuned their radio telescopes towards the galactic center in the mid-20th century, they heard something extraordinary. A roar. A constant flood of radio signals pouring outward from a single, compact point at the exact center of the galaxy. That point had a name, and what it turned out to be would shock the entire field of astronomy. The wall of dust kept the secret for billions of years. Now we were finally about to see what was on the other side. The first radio telescope pointed at the galactic center did not reveal much. A signal. A direction. A general noise coming from somewhere deep inside the plane of the Milky Way. Early radio astronomers in the 1940s and 50s knew something was there, but the technology was too crude to see any detail. It was like hearing a roar from behind a closed door and having no way to open it. So scientists got creative. They built bigger dishes, better receivers, more sensitive equipment aimed at longer wavelengths that could cut through the dust even more cleanly than visible light ever could. Radio waves with wavelengths stretching from the size of a pencil to the size of a football field can travel straight through the densest dust clouds in the galaxy without losing a single bit of energy. The Galactic Center had no defense against them. By the 1970s and 80s, radio maps of the Galactic Center began to take shape. What astronomers saw was unlike anything in the outer galaxy. Bright, tangled filaments of radio emission stretching across the sky like glowing threads. Dense clumps of gas compressed into tight balls. Enormous arcs and loops of material churning in patterns that suggested something incredibly powerful was driving them. But radio waves alone could only show so much. The Galactic Center also hides behind extreme heat and pressure, so scientists turned to a second tool: infrared light. Infrared sits just below red in the spectrum of light, invisible to human eyes but detectable with cooled camera sensors. Unlike visible light, infrared can push through most of the dust and reveal the actual stars lurking inside the core. When the first infrared images of the Galactic Center came through in the 1990s, the reaction was immediate and visceral. There were stars there, thousands of them, packed unbelievably close together. Stars so dense they looked like a city skyline compared to the quiet suburban spacing of stars out here near our sun. And those stars were moving fast, circling, curving, rushing around a central point in tight, violent orbits. That central point was invisible even in infrared, but its effect on everything around it was unmistakable. Astronomers tracked individual stars near the core over years and then decades, mapping their precise paths with the Keck Observatory's giant mirrors in Hawaii. One star, designated Star 2, completed a full orbit in only 16 years, swinging around the invisible central point at speeds of up to 5 million miles per hour. The math was clear. Something with the mass of 4 million suns was packed into a region smaller than our solar system. The curtain cracked, and behind it was the most extreme object we had ever confirmed in our own galaxy. Gamma rays gave astronomers a third set of eyes. High-energy gamma rays pour out of the Galactic Center in quantities that no ordinary star cluster could produce. Entire space telescopes were built specifically to catch them. Each new window into the electromagnetic spectrum revealed another layer of the core's complexity. Each new image looked stranger than the last. The Galactic Center was alive. It was churning. It was radiating energy across every frequency we could measure. And every tool we pointed at it told us that the object at its heart was unlike anything else in the Milky Way. In 1974, radio astronomers detected a tiny, intensely bright point of radio emission at the exact center of the Milky Way. They named it Sagittarius, a star. At the time, nobody could say for certain what it was. The signal was strange and compact, unlike any ordinary star or nebula. It sat completely still, even as everything around it orbited and churned. Decade after decade, astronomers kept watching it, kept measuring it, and kept arriving at the same terrifying conclusion. Sagittarius A star is a supermassive black hole. Its mass equals 4 million of our suns, compressed into a region roughly the size of the distance between the Sun and Mercury. An object that heavy, packed that tightly, creates a gravitational pull so extreme that space itself curves around it. Anything that crosses a certain invisible boundary, called the event horizon, disappears forever. No signal, no light, no information ever comes back out. 4 million solar masses packed into a space our entire solar system would dwarf. For years, this remained a strong inference rather than a direct observation. Scientists could measure the stars orbiting it. They could calculate the mass from those orbits. They could track how gas clouds accelerated as they fell toward it. But they could not take a picture of the black hole itself. Light that close to the event horizon bends, stretches and vanishes before it can escape. Then, in April 2019, a global network of radio telescopes called the Event Horizon Telescope linked together to form a dish effectively the size of Earth. The target was Sagittarius A star. Months of data processing later, scientists released the first actual image of the shadow of our galaxy's central black hole, a glowing ring of superheated gas surrounding a dark circle at the center. The shadow of something so massive that even light cannot orbit it safely. The image confirmed everything the orbital measurements had suggested. What makes Sagittarius A star unusual even among black holes is its current quietness. Supermassive black holes in other galaxies, called active galactic nuclei, shoot enormous jets of energy from their poles as they consume enormous amounts of material. They glow across billions of light years. Our central black hole sits in near silence by comparison. Its feeding rate is low right now. It is, in cosmic terms, sleeping. But the evidence surrounding it tells a very different story about its past. Scars on the surrounding gas clouds, ionization patterns that point to ancient flares of energy, distant structures still glowing from explosions that happened millions of years ago. Sagittarius, a star, was not always this quiet. Something woke it up in the past. Something fed it. And the aftermath of that feeding shaped the entire inner galaxy in ways we are still mapping today. The silence of Sagittarius A star right now gives astronomers a window to study the wreckage it left behind. Every structure within thousands of light years of the core carries some record of what happened when this black hole was active. Every gas cloud, every radiation bubble, every stretched filament of material tells part of the story. And the story begins with the ring of chaos surrounding it. Step back from the black hole, and the chaos only grows. Surrounding Sagittarius, a star is a structure called the central stellar bar, and it is unlike anything in the quiet outer reaches of the Milky Way. A thick, elongated concentration of millions of stars packed far closer together than anything in our solar neighborhood, rotating around the galactic core in patterns that look less like an orderly orbit and more like a slow-motion car crash happening over millions of years. In our part of the galaxy, stars are typically separated by distances of several light years. Our nearest stellar neighbor, the Alpha Centauri system, sits about 4 light years away. Imagine the Sun at one end of a football field and Alpha Centauri somewhere around the 25-yard line. Plenty of space between them. Inside the central stellar bar, that spacing collapses dramatically. Stars crowd together so densely that the night sky from any planet orbiting one of those stars would blaze with thousands of neighbors close enough to see clearly. From inside that region, the sky would never truly go dark. The stars inside the bar do not orbit the galaxy the way our sun does, in a relatively smooth, nearly circular path that takes 225 million years to complete. Inside the bar, stars follow elongated, stretched paths that carry them deep toward the core and then swinging far outward again. Different stars cross each other's paths. Gravitational tugs constantly nudge orbits sideways. The whole structure vibrates with chaotic energy. This is where the story gets complicated. The central stellar bar is not just a collection of old stars left over from the galaxy's formation. New stars form there. Young, massive, brilliant blue stars burn inside the core region at a pace that astronomers find hard to explain, given how hostile that environment is. Intense radiation from the black hole, supernova shockwaves from dying massive stars, and extreme tidal forces from gravity should make star formation nearly impossible that close to the center. And yet it happens. The core keeps making stars. The question scientists argued about for years was where the raw material for those new stars was coming from. Star formation needs gas, cold, dense gas that can clump together, compress under its own gravity, and ignite. The environment around the galactic center should heat and shred any gas before it gets dense enough to collapse. The radiation alone should blow it apart. Something was delivering fresh gas to the core anyway. Something was threading material through the hostile environment and depositing it right where new stars could form. For years, astronomers suspected hidden structures inside the galactic region were acting as pipelines. They just could not find them. The central stellar bar churned on. Stars formed, burned bright, exploded, and fed their material back into the gas supply. A brutal, self-sustaining cycle of creation and destruction operating at the most extreme scales our galaxy could produce. And somewhere inside that dusty, radiation-soaked region, hidden behind layers of gas and stellar debris, something enormous was waiting to be found. A structure so large and so important that missing it for this long seemed almost impossible. Our solar system is quiet, 4.5 billion years old, settled into a smooth orbit around the outer edge of the Milky Way, roughly 100,000 light years from the galactic center. The nearest star is years away at the speed of light. Major gravitational disturbances happen on timescales of millions of years. By cosmic standards, we live in a suburb so calm it barely registers. The galactic center is the opposite of all of that. The density of material in the core region is so much higher than our neighborhood that comparisons feel almost meaningless. Gas clouds there are thousands of times denser than typical interstellar clouds. The radiation environment is so intense that particles get accelerated to energies we cannot reproduce in any particle accelerator on Earth. Magnetic fields twist and snap with energy levels that dwarf anything in the outer galaxy. And the gravity. The gravity changes everything. Out here near the sun, gravitational tides from the galactic center are gentle. We orbit the core the way a boat bobs far offshore from a massive waterfall, aware it exists, unaffected by it directly. Inside the central few thousand light years, tidal forces from the supermassive black hole become a dominant factor in how gas and stars behave. Gas clouds that would collapse peacefully into stars out here near us get shredded by tidal forces before they can compress enough. Stars that would age quietly get their orbits yanked and twisted by the gravitational chaos around them. The timescales of activity also compress dramatically. Events that take billions of years in the outer galaxy happen in millions of years near the core. Star formation cycles run faster. Supernova rates are higher. Material flows and churns and gets recycled at a pace the outer galaxy never matches. One of the clearest signs of this difference is temperature. The gas between stars in our neighborhood runs at roughly minus 440 degrees Fahrenheit, barely above absolute zero. The gas near the galactic center runs orders of magnitude hotter, energized by radiation, shock waves, and the constant friction of material crashing together. Scientists began studying this difference in detail in the late 20th century, using increasingly powerful radio telescopes to map the velocity, temperature, and density of gas clouds across the core. What they found was not a single uniform region of chaos, but a layered, complex system with distinct zones of activity, each feeding into the next, each driving processes that ultimately channeled material inward toward the black hole. The core is a machine, a vast, violent, endlessly cycling engine that converts gas into stars, stars into supernovae, supernovae into shock waves, and shock waves into the next generation of gas clouds. Everything feeds back into everything else. The outer galaxy, where we live, benefits from this engine in ways we are only beginning to understand. Heavy elements forged in the core's massive stars get scattered outward over billions of years. The magnetic fields generated near the center thread outward into the galaxy's arms. Even the structure of the spiral arms themselves may owe something to the gravitational influence of the central bar. We are downstream from the most powerful engine in the galaxy, and we had almost no idea what that engine looked like until very recently. In July 2025, astronomers quietly published a paper that rewrote the map of the galactic center. Hidden inside a region of the galaxy that researchers had surveyed before but never examined at this level of detail, a team of scientists found something enormous. A molecular cloud stretching 200 light years from one end to the other, sitting in a zone between the calm outer disk of the galaxy and the violent inner core. It had no entry in any catalogue. No earlier study had flagged it. For all practical purposes, It was invisible until the right instrument looked in the right way. They named it the Midpoint Cloud, and the more they studied it, the stranger it got. 200 light years is an almost impossible scale to picture. Our entire solar system, from the sun out to the farthest edge of the Oort cloud, spans about 2 light years. The Midpoint Cloud is 100 times wider than that. If you placed it in our neighborhood of the galaxy and stood on Earth, it would span most of the visible sky. It is a structure so large that entire stellar nurseries fit comfortably inside it with room to spare. The cloud sits in a transition zone that astronomers had long known was important but struggled to study in detail. The outer galactic disk is a relatively ordered place where gas and dust follow predictable patterns. The inner core is chaos. The boundary between those two regions, the zone where ordered structure starts breaking down and violent energy takes over, is exactly where the Midpoint Cloud lives. This placement is not an accident. Scientists quickly realize the cloud is doing something critical. Material from the outer disk flows inward toward the galactic center along a set of well-known dust lanes. Narrow channels of dense gas that curve inward toward the core like the arms of a spiral. These lanes had been mapped for decades. What nobody had spotted before was that right at the zone where these lanes transition into the turbulent core environment, an enormous reservoir of gas and dust was accumulating, piling up, building mass. The Midpoint Cloud is that reservoir. Gas flowing inward along the dust lanes hits the chaotic environment of the core zone and slows down. As it slows, it begins to pile up, layer on layer, over enormous timescales, until it forms a structure massive enough to trap more incoming gas and compress it further. The cloud acts as a collection point for the material flowing toward the heart of the galaxy. And once the cloud had enough mass, the math became straightforward. Dense molecular clouds do one thing when they reach a certain threshold. They collapse. Gravity takes over. The cloud fragments into clumps, each clump compressing faster than the last, each one building toward the conditions necessary to ignite a star. The Midpoint Cloud had already reached that threshold in several regions. Stars were about to be born inside one of the most hostile places in the Milky Way. The discovery alone was extraordinary, but the tools that found the cloud revealed something even more dramatic lurking inside it. To find something hidden in the most obscured region of the galaxy, you need an instrument that laughs at dust. The Green Bank Telescope in West Virginia is the largest fully steerable radio telescope on Earth. Its dish spans 330 feet across, roughly the size of a football field standing on its end, mounted on a base that can rotate to point at any position in the sky. It collects radio waves with a sensitivity that makes other radio telescopes look like tin cans on strings. Radio waves are the key. They pass through dust, gas, and molecular clouds without losing energy, carrying information about the structures inside those clouds directly to the receiver at the telescope's focus. The Green Bank Telescope can detect radio signals so faint they carry less energy than a single snowflake hitting the ground. Dr. Natalie Butterfield led the team that pointed this instrument at the transition zone between the galactic disk and the core in the months before the 2025 discovery. The survey she designed was methodical and thorough, covering a region of the sky that earlier surveys had sampled, but never examined at full sensitivity. The goal was to map the molecular gas in that transition zone in more detail than anyone had before. The data came back in enormous files, terabytes of radio measurements encoding the velocity, density, and chemical composition of gas across the target region. Processing that data took months. The team wrote software to untangle the overlapping signals from different clouds at different distances and different speeds. And then the Midpoint Cloud appeared in the data. Massive, unmistakable, stretching across the maps like a continent nobody had drawn before. The reaction inside the team was disbelief first, then careful verification, then growing excitement as every check confirmed the structure was real. This was not a processing artifact. The cloud showed up consistently across multiple frequencies, multiple scan passes, and multiple independent analysis methods. It was real, it was enormous, and it had somehow escaped detection until now. The reason it stayed hidden so long comes down to location and perspective. The midpoint cloud sits along the same line of sight as several other well-known structures in the galactic center region. From Earth, these structures overlap, their radio signals mixing together in ways that make individual components hard to separate. Earlier surveys lacked the sensitivity and resolution to pull the midpoint cloud's distinct signal out of that noise. The Green Bank telescope's combination of size, sensitivity, and careful survey design gave Butterfield's team the edge they needed. A slightly smaller telescope would have missed it. A less carefully designed survey strategy would have blurred it into background noise. The find raised an immediate question. How many other structures of this size are hiding in the galactic center region, waiting for the right instrument to reveal them? The answer, based on what the same survey data suggested, was probably several. The midpoint cloud was the biggest surprise, but the data hinted at other structures in the same zone that deserved closer attention. The galactic center was even less mapped than anyone had realized, and inside the cloud itself, the telescope was detecting signals that pointed to something actively happening right now. Inside the midpoint cloud, there are rivers. Not water rivers. Rivers of dust and gas, dense beyond anything in our neighborhood, flowing in narrow channels through the interior of the cloud. These structures follow paths carved out by gravity and magnetic fields, threading through the cloud's turbulent bulk and funneling material in a specific direction. Inward, toward the galactic center, toward the black hole. Scientists call these channels dust lanes, and they had been known to exist in the broader galactic center region for decades. Massive, sweeping arcs of dense material curving inward from the outer galaxy like the arms of a funnel. But finding evidence of these channels continuing through a newly discovered cloud at the transition zone added a critical piece to the puzzle. The material flowing through the galactic center does not arrive all at once. It travels in stages. Gas in the outer galaxy slowly drifts inward, funneled by the gravitational influence of the central stellar bar. As it reaches the dust lanes, it speeds up, compressed by the narrowing channels. By the time it reaches the midpoint cloud, it carries momentum, density, and a supply of raw material that the cloud captures and holds. Think of it like a river system from above. Broad, lazy tributaries far from the center gradually narrow and deepen as they approach the main channel. The main channel runs fast and full, cutting through the landscape toward its destination. The midpoint cloud is a massive lake fed by those channels, collecting everything the tributaries deliver before the flow continues onward. The dust lanes inside the cloud are not smooth, uniform streams. They are turbulent, clumpy, full of dense knots where gas is compressed tightly enough that it begins to interact with itself. These knots are where star formation begins, where the raw material gets dense enough that gravity takes over from the other forces holding it apart, and collapse becomes inevitable. Astronomers measured the density of these clumps inside the midpoint cloud using the spectral lines of specific molecules, chemical compounds that only form under certain temperature and pressure conditions. The molecular fingerprints in the radio data told the team exactly how dense those clumps were, how cold their cores had become, and how far along the collapse process had progressed. The numbers came back well above the threshold for star formation. Several clumps inside the midpoint cloud were already on the edge of ignition. The dust lanes are not just feeding the cloud, they are feeding a process that will eventually produce an entirely new population of stars deep inside the galactic center region. Stars that will live fast, burn bright, and die violently, adding their own energy and material to the cycle that has been running since the galaxy first formed. And here is what makes this genuinely unsettling. The material flowing through those hidden rivers is feeding the central stellar bar. Some of it will reach the black hole itself. Sagittarius. A star may be quiet right now, But the supply line is open. The rivers are running. The question is, what happens when enough material finally arrives? The midpoint cloud is not stable. Scientists confirmed this after analyzing the density measurements from the Green Bank telescope survey. Several regions inside the cloud have already crossed the line where the outward pressure of gas balances the inward pull of gravity. In those regions, gravity has won. The gas is falling inward on itself, compressing toward the conditions needed to spark nuclear fusion and birth a new star. This process, called gravitational collapse, is the fundamental act of star creation. It happens in molecular clouds across the galaxy every year. But seeing it happen inside a cloud positioned at the edge of the galactic core, in an environment that should make it nearly impossible, forced astronomers to reconsider what they thought they understood about where and how stars form. The galactic center is hostile to star formation in almost every way. Intense radiation from existing massive stars tears apart fragile gas structures. Tidal forces from the nearby black hole stretch and shred clouds before they can compress. Supernova shockwaves from constantly exploding stars blast through the region and heat the gas, driving it apart rather than letting it cool and condense. Under those conditions, the standard textbook description of star formation breaks down completely. You need cold, dense, undisturbed gas to make a star. The galactic center has almost none of those conditions. And yet the evidence is clear. Stars do form there. Young, massive, brilliant stars burn inside the core region in clusters that are too young to have formed anywhere else and migrated inward. Something is overcoming the hostile environment, shielding gas from the worst of the radiation, and allowing collapse to proceed anyway. The midpoint cloud may be part of that answer. Its enormous mass provides a kind of self-shielding effect. The outer layers of the cloud absorb the incoming radiation, protecting denser knots deeper inside from the worst of it. Material that reaches those protected inner regions can cool down enough to begin collapsing before the radiation can penetrate and heat it back up. The cloud acts as its own armor. Scientists are paying close attention to which specific regions inside the cloud show the most advanced signs of collapse. Some of those regions contain what are called dense cores, knots of gas only a fraction of a light year across, where densities are high enough that normal molecular chemistry breaks down entirely. These are the direct precursors to new stars. When those dense cores finally ignite, the resulting stars will be massive. Stars forming in environments with this much available gas and this much pressure tend to run large. Massive stars live fast and die young, burning through their fuel in millions of years rather than billions. Their deaths in supernova explosions will pump enormous energy back into the surrounding cloud, triggering further collapse in other regions, setting off a chain reaction of starbirth through the rest of the midpoint cloud's bulk. The whole thing is a compressed trigger, and it is already pulled. Something even stranger is happening at the points where those collapses are most advanced. Deep inside the midpoint cloud, certain spots are screaming. The Green Bank telescope picked up intense bursts of microwave radiation from specific locations within the cloud, sources far brighter than any ordinary background emission. These signals come from a phenomenon called masers, an acronym for microwave amplification by stimulated emission of radiation. A maser is a natural version of what a laser does with light, except operating with microwave energy instead. Under the right conditions of density, temperature, and chemical composition, clouds of specific molecules can amplify incoming microwave radiation and emit it in a tight, powerful beam. Masers require very specific conditions to operate. They need dense gas. They need a strong energy source nearby to excite the molecules. And they need those molecules to be in a particular chemical state that allows amplification to happen. Those conditions occur naturally in only a handful of environments in space, and the most common one is the region immediately surrounding a newly forming star. Finding masers inside the midpoint cloud is therefore a direct signal that star formation is already active at those locations. The masers are not just a random phenomenon, They are beacons marking the exact spots where new stars are being born right now. The specific molecules producing the mesa signals in the midpoint cloud are water and methanol, compounds that form in dense molecular gas when energized by a nearby heat source. Their presence in those quantities at those locations tells scientists that protostars, objects in the earliest stages of stellar birth, are already generating enough heat and radiation to excite the surrounding gas into massive emission. This matters because it is direct, real-time confirmation of what the density measurements only implied. The cloud does not just look like it is on the verge of star formation, it is actively forming stars. The lighthouses are already lit. Each massive location inside the midpoint cloud corresponds to a region where a protostar is building mass by drawing in surrounding gas. The protostar heats its cocoon of infalling material, which glows in infrared. The densest layers of that cocoon produce the mesa emission that the Green Bank telescope detected. Some of these protostars will ignite fully in the coming tens of thousands of years. Others may stall if the environment disrupts their gas supply before they accumulate enough mass. But the ones that make it through will be giants. Massive, luminous, and violent in their eventual deaths. The masses also hint at something larger about the cloud's internal structure. Their distribution across the midpoint cloud's extent is not random. They cluster in specific zones that align with the densest sections of the dust lanes mapped by the survey. The hidden rivers inside the cloud are not just flowing. They are depositing material in specific nodes where collapse and star formation are already underway. The midpoint cloud is active across its entire length. Multiple star nurseries operating at once. Multiple protostellar objects igniting in an environment that should not allow any of them to exist. What the telescope also found in the same region was not just birth. The galactic center is full of scars. Alongside the active star nurseries and the glowing mesa sources, the Green Bank telescope survey mapped a different kind of structure inside the midpoint cloud region. Large, hollow shells of gas, tens of light years across, carved into the surrounding material by forces that came from within. These shells are the remnants of supernovae, the explosions that end the lives of the most massive stars. When a star with many times the mass of our sun runs out of fuel, its core collapses in an instant and then rebounds outward in a detonation that briefly outshines entire galaxies. The blast wave from that explosion travels at tens of thousands of miles per second, slamming into the surrounding gas and sweeping it outward into a growing bubble of hot, compressed material. Over thousands of years, that bubble expands, cools, and eventually merges with the surrounding interstellar medium. What it leaves behind is a shell, a thin, hollow ring of gas marking the boundary where the blast wave finally ran out of energy. In radio observations, these shells glow distinctly from the surrounding material, their compressed edges lighting up against the background. The Milky Way contains hundreds of these supernova remnants scattered across its disk. Finding several of them clustered inside and around the midpoint cloud is consistent with what the mesa signals already suggested. This region has been cycling through star formation and stellar death for a long time. Previous generations of massive stars formed here, burned bright, and then exploded, leaving these hollow monuments to their deaths. Each explosion did more than just leave a shell. The blast wave from a supernova compresses the surrounding gas as it expands. That compression can trigger new rounds of star formation in the gas it sweeps up, creating a chain reaction where one stellar death causes the birth of the next generation. Scientists call this triggered star formation, and the shells inside the midpoint cloud may be evidence of exactly that process playing out over millions of years. The shells also pump energy into the cloud's internal turbulence. The kinetic energy of a supernova blast wave is staggering, roughly 10 to the power of 44 joules, released in seconds, and a significant fraction of that energy goes into driving shockwaves through the surrounding gas. Those shockwaves stir the cloud, prevent it from settling into uniform density, and create the kind of turbulent, compressed clumps where the next round of star formation can begin. Death feeding birth, explosions triggering creation. The midpoint cloud is not just a passive reservoir of gas, it is an active processing environment where the cycles of stellar life and death are running simultaneously. But these shells and nurseries exist inside the cloud at a relatively contained scale. The story of what happens to the energy and material that escapes the cloud and reaches farther outward is a completely different order of magnitude. Because beyond the midpoint cloud, the galactic center has been building something so large, it covers nearly half the sky. How does anything survive long enough to become a star in a place like this? The galactic center bombards everything with radiation. Shock waves blast through the gas every few thousand years from yet another supernova. The black hole's gravity pulls on nearby clouds, stretching and shredding them. Magnetic fields 10,000 times stronger than anything near our sun thread through the gas and resist compression. The environment is an obstacle course for any gas cloud trying to collapse into a star. And yet, the evidence inside the midpoint cloud proves it is happening. The masses are lit. The dense cores are compressing. The protostars are building mass. Something is allowing star formation to proceed despite everything working against it. Part of the answer is mass. The midpoint cloud is heavy enough that its own gravity competes with all the forces trying to disrupt it. A small, lightweight cloud near the galactic center would get shredded in thousands of years. A cloud massive enough to hold itself together against tidal forces, radiation pressure, and supernova shockwaves can survive long enough for collapse to begin in its densest regions. Mass is armor. Another part of the answer is magnetic fields. This sounds counterintuitive because strong magnetic fields generally resist compression. But in specific conditions, magnetic fields can actually channel gas along their lines, funneling it into dense streams that concentrate material faster than simple gravitational collapse alone could manage. Inside the midpoint cloud, the magnetic field structure threading through the dust lanes may actually be helping concentrate gas into the nodes where star formation is happening. The third part of the answer is speed. Stars forming in the galactic center have to form fast. They do not have the luxury of slowly condensing over tens of millions of years the way stars do in quieter regions. If a dense core does not reach ignition quickly, the next shockwave or radiation burst will heat it back up and end the process. The extreme pressures inside the midpoint cloud accelerate collapse timescales, compressing gas into protostars faster than anywhere else in the galaxy. Stars formed under these conditions come out different. They tend to be massive because the abundant gas supply and high-pressure push cores to accumulate more material before ignition. Massive stars burn hotter and faster. A star 10 times the mass of our sun burns its fuel roughly 10 million times faster proportionally, living only a few million years instead of billions. These stars are born in violence and die in it too. Their short lives produce enormous amounts of ultraviolet radiation that ionizes the surrounding gas, creating glowing regions called H2 regions that can be seen across the galaxy. Their deaths in supernovae add more shells to the already scarred landscape of the galactic core. Every star born inside the midpoint cloud is a future explosion waiting to happen. Every future explosion will stir the gas, trigger new collapses, and keep the cycle running. The core is not just a place where stars go to die, it creates its own violent future, generation after generation, feeding a machine that runs on the most extreme forms of energy in the galaxy. And that machine produces something even bigger than any star. Step back from the galactic center far enough, and you would see something no human eye was designed to detect. Two enormous bubbles of energy extending above and below the plane of the Milky Way, stretching outward from the galactic core like the two lobes of a dumbbell, each one tens of thousands of light years tall. Together they span a distance so vast that our entire solar neighborhood would fit inside one of them thousands of times over. They glow in gamma rays, the most energetic form of radiation in the universe, completely invisible to human sight, but blazing in the data from space-based telescopes. These are the Fermi bubbles, and when astronomers first confirmed their existence in 2010, the discovery shook the field. The Fermi Gamma Ray Space Telescope launched in 2008 with the goal of mapping high-energy radiation across the entire sky. Its detectors count individual gamma-ray photons arriving from space, building up a picture of the gamma-ray universe, one particle at a time. Within 2 years of operation, the telescope had gathered enough data that a team led by scientists at Harvard and NASA began noticing something unexpected in the maps of the Milky Way region. Faint at first, then unmistakable as the data accumulated, 2 enormous glowing regions appeared above and below the galactic plane. Their edges were sharper than diffuse background radiation should be. Their brightness was more uniform than random particle acceleration would produce. They looked like structures, bounded and shaped, as if something had blown 2 colossal bubbles out of the galactic center and left them hanging there. They named them after the telescope that found them. The size of the Fermi bubbles is hard to communicate without a comparison that makes the scale visceral. Our Sun is about 93 million miles from Earth. The nearest star is about 25 trillion miles away. The Milky Way's disk is roughly 600 quadrillion miles across, and each Fermi bubble extends about 294 quadrillion miles from the galactic plane, covering nearly half the sky when viewed through gamma-ray instruments from Earth. From one end of the bubble structure to the other, the total span roughly matches the diameter of the visible disk of the entire galaxy. These structures are so large that 2 well-known star patterns in opposite ends of the night sky mark their rough boundaries. Standing in the southern hemisphere on a clear night, the constellation Virgo sits near the top of the upper bubble. The constellation Grus sits near the bottom of the lower one. The Fermi bubbles frame a significant portion of our visible sky, and for decades before their discovery, nobody knew they were there. The reason they escaped detection for so long is the same reason the galactic center stays hidden from optical telescopes: the wrong tools. Visible light and radio waves do not reveal gamma-ray structures. Only a gamma-ray space telescope, built specifically to catch the highest energy photons in the universe, could make them visible. Before the Fermi telescope, astronomers had no instrument sensitive enough to map them in detail. Their discovery raised an immediate and urgent question. Something produced 2 galaxy-spanning bubbles of gamma radiation. What was it? Imagine lying on your back in a field at night, staring up at the Milky Way arching overhead. Now imagine that hidden in that same sky, stretched across the band of light from the constellation Virgo high above you all the way down to the constellation Grus near the southern horizon, 2 enormous bubbles of gamma radiation are glowing with the energy equivalent of 100,000 supernova explosions. Billions of miles across in every direction, pulsing with radiation at energies that would shred human cells in seconds. You cannot see them, but they are there, right now, tonight, filling a huge portion of the sky above and below the Milky Way's disk. The Fermi telescope detected them because it was specifically built to catch gamma-ray photons, particles of light with energies roughly 1 billion times greater than the visible light your eyes detect. When those photons arrive at Earth after traveling tens of thousands of light years from the bubble walls, the telescope's detectors register each one individually. Building up a map of where those photons come from took months of operation. The pattern that emerged was unmistakable. The bubbles are roughly round, their edges are surprisingly sharp, more like the walls of an inflated balloon than the diffuse fuzzy borders of a natural radiation zone. Inside the bubbles, the gamma-ray brightness is relatively uniform. That combination of sharp edges and uniform interior brightness told astronomers these structures were physically bounded, inflated from the inside by some ongoing energy process, rather than simply scattered radiation drifting outward from the core. Whatever created the Fermi bubbles pushed energy outward uniformly in all directions, above and below the galactic disk, at a rate sustained long enough to inflate structures of this size. That is an almost incomprehensible requirement. The energy budget for inflating the Fermi bubbles, calculated from their size and the brightness of their gamma ray emission, runs into numbers that only the most extreme events in galactic history can produce. A team of astronomers spent years after the 2010 discovery analyzing the bubble walls in detail. They measured the speed of gas at the bubble boundaries using ultraviolet observations from separate space telescopes. That gas was moving outward from the galactic center at speeds of several hundred miles per second. Not drifting, racing outward, driven by an internal pressure still pushing from within. The bubbles are still expanding, slowly by human standards, but steadily. Whatever inflated them has either not stopped entirely or left behind a residual energy that keeps the walls moving. That boundary between inside and outside the bubble is also where some of the most intense particle acceleration in the galaxy happens. Cosmic rays, protons, and electrons moving at near the speed of light slam into the dense gas at the bubble walls and produce gamma rays through a process called inverse Compton scattering. The bubble walls are particle accelerators running continuously across a region larger than the distance from Earth to the nearest stars. The scale of this structure forces a simple question: what in our galaxy has enough energy to do this? The answer splits astronomers into two camps, and the debate has never been fully settled. Numbers alone do not work here. Saying the Fermi bubbles span 50,000 light-years tells you a distance. It does not tell you what that distance feels like, or why it should make you stop whatever you are doing and reconsider how small our corner of the universe really is. So try this instead. The space shuttle, the fastest vehicle humans ever regularly operated in orbit, traveled at about 17,000 miles per hour. At that speed, a trip from Earth to the Moon takes roughly 14 hours. A trip to Mars at its closest approach takes about 5 months. A trip to the edge of our solar system takes about 30 years. A trip to the edge of the nearest Fermi bubble at space shuttle speed would take roughly 2 billion years. The bubble you're traveling toward is part of a structure that formed because of events at the center of the Milky Way. It is a physical consequence of our galaxy's own history, inflated by forces operating at the core we already examined. Pushed outward at speeds of hundreds of miles per second, and sitting far above and below the galactic plane like the remnant of a detonation so powerful it left marks that will persist for millions of years into the future. Astronomers who study the Fermi bubbles use the word extraordinary with unusual frequency. These are people trained to stay calm about extreme phenomena. Gamma ray bursts, neutron star collisions, quasars burning from the opposite edge of the observable universe. The Fermi bubbles make this group pause. The reason is context. Other enormous gamma ray structures exist in the universe. Active galaxies with supermassive black holes consuming material at high rates routinely produce jets and lobes of radio and gamma ray emission. Some of those structures dwarf the Fermi bubbles. They are not unique in the universe. They are unique in our galaxy. The Milky Way was thought to be a quiet, middle-aged spiral with a dormant central black hole and no active large-scale energy structures. The discovery of the Fermi bubbles proved that picture wrong. Our galaxy carries the scar of a past event so energetic it produced structures that will outlast civilizations. Understanding what made them requires going back to the galactic center and asking what was different there millions of years ago compared to now. The current silence of Sagittarius A star provides a strange contrast. The black hole sits relatively dormant, consuming very little material, producing no jets, emitting no extraordinary amounts of energy. If you arrived at the galactic center today with no knowledge of history, you might conclude nothing dramatic had ever happened there. The Fermi bubbles tell a completely different story. Something happened. Something enormous. Something that pushed enough energy into the galactic halo to inflate two bubbles the size of the galaxy's disk and keep them glowing in gamma rays for millions of years afterward. Two explanations compete for that role, and astronomers have been arguing about which one is right ever since 2010. Two theories, one winner eventually, but the debate has lasted 15 years and still has not been fully settled. The first theory points directly at Sagittarius A star. Black holes that actively consume material do not just pull matter in, they also push energy out. As gas falls toward a black hole, it forms a spinning disk of superheated material called an accretion disk. That disk radiates enormous amounts of energy, and in many cases, some of that energy gets redirected by magnetic fields into narrow jets of particles and radiation shooting outward from the black hole's poles at near the speed of light. Galaxies with active black holes, called quasars, and active galactic nuclei produce jets powerful enough to be seen from billions of light years away. If Sagittarius A star entered an active phase millions of years ago, consuming a large amount of gas in a relatively short time, it could have produced jets energetic enough to inflate structures the size of the Fermi bubbles. The jets would have blasted outward from the galactic plane, pushing gas and energy into the galactic halo, inflating the bubbles from the inside as they expanded outward. Evidence supporting this idea includes the relatively sharp edges of the Fermi bubbles and the fact that their geometry is symmetrical above and below the galactic plane, exactly what you would expect from two jets firing in opposite directions from a central point. The second theory points not at the black hole but at a burst of star formation in the galactic core. Massive stars release their energy in supernovae and stellar winds. If thousands of massive stars formed in the central few thousand light years, in a relatively short burst millions of years ago, their combined energy output, released over millions of years through winds and explosions, could have driven an outflow powerful enough to inflate the Fermi bubbles. This theory, called the starburst hypothesis, also fits the bubble geometry and the energy budget. The central stellar bar contains evidence of past bursts of star formation. The sheer number of older stars in the core suggests periods of rapid formation that are not happening at the same rate today. Both theories predict bubbles of roughly the right size and brightness. Both have supporting evidence. Both have problems. The black hole jet theory requires Sagittarius A star to have been thousands of times more active than it is today, a transition that should have left additional specific signatures that are harder to confirm. The starburst theory requires a burst of star formation more intense than anything astronomers have directly observed elsewhere in the Milky Way. A third possibility, discussed less often, is that both happened. A burst of star formation drove an initial outflow, and then the black hole activated afterward and added its own energy to the already expanding structure. The Fermi bubbles might be the combined scar of two separate extreme events, not one. The answer might be hiding in the energy signature at the galactic center itself, because something there is producing radiation at levels that no clean version of either theory fully accounts for. The galactic center is not just producing energy, it is collecting it. In 2016, a network of ground-based telescopes spread across Namibia, called the High Energy Stereoscopic System, completed an analysis of something unusual they had been tracking in gamma-ray data from the inner galaxy. What they found was a diffuse glow of gamma radiation spread across the central, few hundred light-years of the galactic core. Not concentrated in any single source, not a point. A broad, continuous shimmer of high-energy emission coming from the gas clouds themselves. The energy level of that emission pointed to particles with energies reaching 50 trillion electron volts. An electron volt is a unit of energy so small that millions of them together barely make a visible spark. 50 trillion of them packed into a single particle represents an energy scale far beyond what any particle accelerator on Earth has ever achieved. For comparison, the Large Hadron Collider in Switzerland, the most powerful particle collider ever built, accelerates protons to energies around 13 trillion electron volts. The galactic center is producing particles nearly 4 times more energetic than our best machine can manage. These particles are protons, the same positively charged particles that make up the nuclei of atoms. They travel at speeds indistinguishable from the speed of light. And they are trapped. The dense gas clouds surrounding the galactic center act as a cage. When a proton traveling at near light speed slams into a nucleus of hydrogen or helium gas, the collision produces pions, unstable particles that decay almost instantly into gamma rays. The galactic center is full of gas. The gas is full of protons slamming into it. The result is a continuous flood of gamma rays pouring outward from the inner core. Scientists confirmed the trapping mechanism by measuring how the gamma ray brightness varied with distance from the center. The brightness fell off with distance in a pattern consistent with a large population of protons distributed through the gas and continuously producing gamma rays by collision. The pattern implied that protons were being injected into the central region and then held there long enough to collide with the gas rather than escaping freely into the galaxy. Something at the center is both accelerating protons to extraordinary energies and preventing them from escaping. The most likely source of both effects is the combined electromagnetic environment of the galactic core. Strong magnetic fields thread through the core region, and magnetic fields deflect charged particles. A proton moving through a magnetic field follows a curved path rather than a straight line. In a region dense enough with magnetic fields, the proton curves, turns, curves again, and effectively gets bounced around inside the magnetic structure rather than streaming outward. Meanwhile, the sources accelerating the protons in the first place are probably the shock waves from supernovae and the powerful stellar winds from the massive stars we already know exist in the core. Every supernova blast wave is a particle accelerator. As the shock wave expands, charged particles bounce repeatedly across the wavefront, gaining energy with each crossing. In a region where supernovae occur far more frequently than in the outer galaxy, the particle acceleration runs continuously. The galactic center produces the highest energy particles in the Milky Way, then holds them captive, turning them into a permanent source of gamma radiation. And that radiation carries fingerprints pointing to something even bigger. Something broke loose from the galactic center millions of years ago. The evidence sits in the structure of gas clouds across the inner galaxy, in the ionization patterns of distant gas, and in the very shape of the Fermi bubbles themselves. Piece by piece, astronomers assembled a picture of an event so powerful that its effects are still visible today, encoded in the scars left across thousands of light years of space. The first major clues came from ultraviolet observations of gas at high latitudes above the galactic plane. Gas that sits far from any obvious energy source should be cold and neutral. Instead, astronomers found it ionized, stripped of electrons, as if blasted by an intense flood of radiation at some point in the past. The ionization pattern pointed back toward the galactic center, like a cone of damage spreading outward from a single origin point. Researchers at the Sydney Institute for Astronomy began piecing this together using data from multiple telescopes covering different wavelengths. What they reconstructed was the signature of a flare, a sudden and massive release of ionizing radiation from Sagittarius A star that fired outward along the galaxy's poles roughly 3.5 million years ago. 3.5 million years ago, our ancestors were walking the plains of Africa on 2 legs. The universe was not much different from today. But at the center of the Milky Way, something very different was happening. The black hole was active. Sagittarius A star, currently consuming almost nothing and producing almost no detectable output, was at that point devouring gas at a rate high enough to produce a sustained, brilliant flare of radiation. The flare shot outward from both galactic poles, traveling at the speed of light, ionizing everything it touched as it went. Gas clouds thousands of light years away got blasted. The radiation cones spread outward, thinning but still powerful enough to leave permanent marks on the gas it hit. The event lasted a relatively short time by cosmic standards, perhaps a few 100,000 years, long enough to ionize enormous volumes of gas, long enough to contribute significant energy to the structures we now call the Fermi bubbles, and long enough to send a signal so powerful it crossed tens of thousands of light years and reached something completely outside the Milky Way. The timing matters. 3.5 million years ago falls within the range suggested by other analyses of the Fermi bubbles' age. If the ancient flare contributed to inflating the bubbles, the two stories connect. The black hole activated, fired a sustained burst of energy along its poles, and drove the expansion that built the structures still glowing in gamma rays today. The dormant black hole of the present looks very different from the active engine of 3.5 million years ago. And between those two states, the galaxy changed. The flare left behind more than ionized gas and inflated bubbles. 3.5 million years of travel at the speed of light covers an enormous distance. Light travels roughly 6 trillion miles in a single year. 3.5 million years of travel adds up to a distance so large that it reaches well beyond the boundaries of the Milky Way's main disk, and into the surrounding space where small companion galaxies orbit our own. That is exactly where astronomers found the next piece of evidence. The Magellanic Stream is a ribbon of gas stretching across hundreds of thousands of light years of space, trailing behind two small galaxies called the Large Magellanic Cloud and the Small Magellanic Cloud. These two dwarf galaxies orbit the Milky Way at a distance of roughly 160,000 light-years from Earth. As they move through space, their mutual gravitational interaction and the tidal pull of the Milky Way strip gas from their outer edges, leaving behind a long, curving trail of hydrogen that stretches across a huge portion of the southern sky. The Magellanic Stream is old. The gas in it has been drifting in space for hundreds of millions of years. It sits far from any significant energy source. It should be cold, neutral, and undisturbed. Astronomers examining the stream in ultraviolet light found something unexpected. Portions of the stream were ionized, their hydrogen atoms stripped of electrons in the same way as the high-latitude gas above the Milky Way's plane. The ionization pattern in the stream matched a specific geometry. The gas closest to the cone of the ancient galactic center flare showed the strongest ionization, and it faded with distance from that alignment. The ancient blast from Sagittarius A star had reached the Magellanic Stream. The radiation cone fired from our galaxy's central black hole 3.5 million years ago traveled across 160,000 light-years of space, crossed the gap between the Milky Way and its companion galaxies, and deposited enough energy into the Magellanic Stream to ionize a significant fraction of its hydrogen. An explosion at our galaxy's core left a visible mark on a neighboring galaxy's gas trail. This is the kind of result that forces a complete reassessment of what galactic centers can do. The conventional picture of a galaxy treats it as a self-contained system. The disk, the halo, the surrounding gas, all evolving together but not dramatically affecting neighboring systems. The Magellanic Stream evidence destroys that picture. A single event at our galaxy's core reached across extragalactic distances and altered the physical state of gas belonging to a completely separate system. The energy required to ionize that much gas across that distance, accounting for the spreading of the radiation cone over light years of travel, implies a source output during the active period that would make Sagittarius A star briefly comparable to much more energetic active galactic nuclei in distant galaxies. Our quiet black hole, for a few 100,000 years, blazed. And the evidence of that blaze, preserved in cold gas hundreds of thousands of light years away, is still readable today. The Magellanic Stream carries a record that cannot be faked. When astronomers study ionization in distant gas, they are reading a signal that was set at a specific moment in time and then preserved. Gas that gets ionized by a burst of radiation stays ionized until it recombines with electrons, a process that takes a specific amount of time depending on the gas density. By measuring how ionized the Magellanic Stream gas still is today, and calculating how long recombination should take at those densities, researchers can work backward to figure out when the ionizing event happened. The The numbers pointed to a few million years ago, consistent with the timeline derived from the galactic center explosion evidence independently. Two completely separate lines of investigation, one tracing ionized gas above the galactic plane and one measuring the ionization of the Magellanic Stream, arrived at the same answer. A powerful flare from Sagittarius A star fired outward several million years ago. Both datasets carry the fingerprint of that same event. Scientists call this kind of preserved historical record a fossil signal. The gas did not forget what happened to it. It is still carrying the mark of that ancient radiation flood, slowly recombining, slowly returning to its neutral state, but still readable if you know what to measure. The Magellanic Stream is functioning as a fossil record of our galaxy's violent recent past. This concept changes how astronomers think about studying galactic history. The standard tools for investigating the past of a galaxy focus on its stars, its structural features, and its light emission. But the gas that surrounds and trails nearby companion galaxies holds another archive entirely. Every powerful event at a galaxy's center leaves fingerprints in the gas within its range. Reading those fingerprints reconstructs events that happened millions of years before any telescope existed to watch them directly. The Milky Way's fossil record, spread across the Magellanic Stream, is among the clearest such records identified around any galaxy. The reason is partly luck. The stream's geometry puts it directly in the path of the radiation cone fired from the galactic poles. The stream happened to be in the right position at the right time to catch the full blast. A gas cloud positioned at a different angle would have received far less radiation and left a much weaker signal. Astronomers are now using this technique to look for similar fossil signals in other gas structures around the Milky Way. If the ancient flare from Sagittarius A star was powerful enough to reach the Magellanic Stream, it was probably powerful enough to leave marks on other gas clouds closer to the galactic center as well. Mapping all of those marks together would give researchers a detailed reconstruction of exactly how the flare evolved over time. When it started, how bright it got, and how it faded. The galactic center keeps talking to anyone who knows how to listen. What it says about the past is extraordinary. What it suggests about the future is something else entirely. Sagittarius. A star is quiet today. Its accretion rate, the amount of material it actively consumes, is astonishingly low for an object of its mass. Most of the gas that drifts close enough to feel its gravity never actually falls in. It gets heated, deflected, or blown back outward before crossing the point of no return. The black hole sits at the center of all that turbulent activity and consumes, by cosmic standards, almost nothing. This might seem reassuring. A dormant black hole at the center of our galaxy sounds better than an active one. And in practical terms, for anything living in the outer galaxy right now, the low activity level of Sagittarius A star is genuinely irrelevant to daily life. The distance between the galactic center and our solar system, roughly 26,000 light years, means that even a significant increase in black hole activity would have no direct physical effect on Earth, for at least that many years, as the radiation would take that long to travel. But the dormancy is not a permanent state. The evidence from the ancient flare proves that. Sagittarius A star has been in active phases before. Multiple lines of evidence suggest it has flared at least once in the last few million years, and the structures surrounding it imply it was far more active in its earlier history. The current quiet period is a pause in a longer pattern of activity. What triggers these active phases? The answer comes back to gas supply. A black hole consumes material when material falls toward it. Sagittarius A star today has a very limited supply of infalling gas in its immediate vicinity, which is why it consumes so little. But the galactic center is not static. Gas clouds migrate inward over time. Stars occasionally pass close enough to the black hole that tidal forces shred them completely, dumping a surge of material into the accretion zone. The midpoint cloud is delivering a fresh supply of gas to the central bar. some of which will eventually work its way inward toward the black hole. None of this happens on human timescales. The processes that could reignite Sagittarius A star to active levels operate over millions to tens of millions of years. The black hole may well remain in its current quiet state for longer than our species has existed. But the galaxy is old and patient. On its timescale, the question is not whether Sagittarius A star will become active again. The question is what that activation will look like when it happens. Past activity produced the Fermi bubbles, ionized gas across the galactic halo, and sent a radiation wave powerful enough to reach a neighboring galaxy's gas trail. Future activity, fed by the rivers of gas currently flowing inward through structures like the midpoint cloud, may produce something comparable. The engine is refueling. The sleeping giant stirs on timescales we cannot watch directly, but the evidence of what it did last time is written across the entire sky. 15 years after the discovery of the Fermi bubbles, the argument over what created them remains genuinely unresolved. Both main theories, the black hole flare and the starburst explosion, survive contact with the available data. Neither has been ruled out. Each predicts features that match observations, and each predicts features that require some adjustment or additional assumption to fit the evidence. The debate is not one side clearly winning. It is two legitimate scientific explanations competing on nearly equal footing. The black hole flare theory got a significant boost from the Magellanic Stream ionization evidence. The geometry of the ionized gas in the stream fits a collimated jet or cone of radiation fired from a central point along the galactic poles far better than it fits a diffuse outflow from many scattered supernovae. If thousands of stars across the central bar each contributed energy to the outflow, the resulting radiation field would be broad and messy. The ionization cone preserved in the Magellanic Stream is structured. It has clear edges. That structure points more naturally toward a single, powerful central source. The starburst theory has its own strong evidence. The chemistry of the gas at the Fermi bubble walls contains signatures of supernova-driven winds, specific elemental abundances, and ionization states that match what you get when stellar winds and supernova explosions drive gas outward. A jet from a black hole would produce a somewhat different chemical signature. The bubble wall chemistry leans towards stellar processes rather than a pure black hole origin. The most honest position in the scientific community is that the Fermi bubbles probably have a complex origin. The galactic center is not a simple system with a single dominant process. Multiple extreme phenomena operate simultaneously. The black hole, massive star formation, supernova explosions, powerful stellar winds, strong magnetic fields. Any event powerful enough to produce structures the size of the Fermi bubbles likely drew on several of these energy sources acting together or in sequence. A burst of star formation could have driven the initial outflow, pushing gas upward from the galactic plane and beginning the inflation of the bubbles. Then an activation event from Sagittarius A star, perhaps triggered by the same gas supply that fed the starburst, could have added a collimated blast of radiation and particle energy that reinforced and structured the growing bubbles. The result would carry signatures of both origins, which is exactly what astronomers observe. This complexity is frustrating from a clean narrative standpoint. Scientists want a single, clear answer. The data keeps suggesting the answer involves more than one driver working at overlapping timescales. Resolving the debate requires either finding a definitive signature that distinguishes black hole jet energy from starburst energy in the bubble walls, or discovering additional historical records, like the Magellanic Stream evidence, that constrain the timeline and geometry of the event more precisely. New telescopes currently under development may provide that resolution. Until then, both theories stand. And while astronomers debate the origin of the bubbles, a completely separate mystery at the galactic center has been deepening for over a decade. The Fermi telescope did not just find the bubbles. After mapping the gamma-ray sky for years, the telescope's data revealed something smaller in angular size but far more puzzling in origin. A concentrated excess of gamma-ray emission coming from the very center of the galaxy. Within the inner few hundred light years around Sagittarius, a star itself, bright, uniform, spherically distributed around the core, a glow that the standard models of high-energy astrophysics could not account for. Astronomers call it the Galactic Center Gamma Ray Excess, and it has been resisting explanation since researchers first confirmed it around 2014. The excess sits on top of all the known gamma ray sources in the region. Subtract the known contributions from pulsars, cosmic ray interactions, and diffuse radiation, and a residual signal remains. Steady, consistent, pointing inward toward the black hole with a brightness profile that follows a specific mathematical curve. That curve matters enormously. The way brightness varies with distance from the galactic center encodes information about where the gamma rays are coming from and what is producing them. The excess follows a profile that fits two very different physical explanations equally well. The first is an unresolved population of millisecond pulsars, rapidly spinning dead stars left behind by supernova explosions, distributed through the inner galaxy in a spherical cloud around the core. Millisecond pulsars produce gamma rays at energies consistent with the excess. If enough of them cluster near the galactic center, their combined emission could produce a signal indistinguishable from what Fermi observed. The second explanation is dark matter. Dark matter makes up roughly 27% of all the mass in the universe. It interacts through gravity, affecting how galaxies rotate, how galaxy clusters bend light, and how large-scale cosmic structures form. Despite being the dominant form of matter by mass in the universe, it has never been directly detected. No experiment on Earth or in space has ever caught a dark matter particle in a way that confirmed its identity beyond doubt. One class of dark matter candidates, called weakly interacting massive particles, would produce gamma rays when two of them collide and annihilate each other. The energy of those gamma rays would depend on the mass of the particle. Theoretical calculations predict that the annihilation signal would have exactly the spherically symmetric profile centered on a massive gravitational source that the galactic center excess displays. The galactic center is the densest concentration of dark matter in the Milky Way. If dark matter particles annihilate each other at some rate proportional to their density, the highest rate of annihilation would occur at the center, where they are most concentrated. The resulting signal would glow most brightly at the core and fade outward, exactly as observed. Both explanations fit the data. Both are scientifically plausible, and the stakes of choosing correctly could not be higher. If dark matter is annihilating at the galactic center, the reason comes down to gravity. Sagittarius, A star's 4 million solar masses of gravitational pull, does not just affect gas and stars. Dark matter, which fills the galaxy in an invisible halo extending far beyond the visible disk, also responds to gravity. In the outer galaxy, dark matter is spread relatively evenly through the halo. But near an enormous concentration of mass like the central black hole, dark matter gets pulled inward and compressed into a structure called a dark matter spike. A spike is exactly what it sounds like. As you move closer to the black hole, the dark matter density does not just increase gradually. It rises steeply, dramatically, following a mathematical profile that concentrates an enormous amount of dark matter into a relatively small volume around the black hole. The closer you get to the event horizon, the denser the dark matter becomes. Dense dark matter means more collisions between dark matter particles. More collisions mean more annihilations. More annihilations mean more gamma rays. A dark matter spike around Sagittarius. A star would produce a gamma ray signal strongest at the very center and fading outward, exactly matching the profile of the galactic center excess. This possibility got serious attention after the 2014, when researchers calculated that the brightness profile of the excess matched certain dark matter particle masses remarkably well. Particles with masses in the range of 30 to 50 times the mass of a proton, annihilating through specific channels, produced signals that lined up closely with the Fermi data. The idea generated enormous excitement. Detecting a dark matter annihilation signal would be one of the most significant discoveries in the history of physics. It would confirm the particle nature of dark matter, measure its mass, identify its interaction channels, and open an entirely new field of observational dark matter physics. Every major physics institution on the planet would immediately refocus resources toward understanding what that signal implied. The excitement was tempered by the millisecond pulsar alternative. The two explanations produce signals that are frustratingly similar in the Fermi data. Distinguishing them requires either finding individual millisecond pulsars in the inner galaxy and counting whether there are enough of them to account for the excess, or finding some feature of the signal that dark matter annihilation predicts and pulsars cannot produce. Both approaches are actively underway. Radio telescopes are scanning the inner galaxy for individual pulsars. Theoretical physicists are working out increasingly precise predictions for what a dark matter annihilation spectrum should look like at specific particle masses. The James Webb Space Telescope and future gamma-ray observatories are adding new data about the inner galaxy's stellar populations. The answer may come within the next decade, or it may require instruments that do not yet exist. Either way, the Galactic Center is the best natural laboratory in the galaxy for this question. Nothing else concentrates dark matter, gamma-ray emission, and observational data in one location the way the inner Milky Way does. One of those answers would confirm known physics. The other would break it wide open. Every physics textbook on Earth would need a new chapter. Confirming that the Galactic Center gamma-ray excess comes from dark matter annihilation would tell us something that decades of underground detectors, particle colliders, and space telescopes have failed to establish. What dark matter actually is. The mass of the particle, its interaction strength, the channels through which it annihilates, all of that information is encoded in the precise energy spectrum of the gamma-ray excess. Reading that spectrum carefully enough would hand physicists a particle profile, essentially a fingerprint for the dark matter particle that theorists could then match to candidate particles from various extensions of known physics. The match would point toward a specific theoretical framework that explains why dark matter has the properties it has, and how it fits into the broader structure of fundamental forces. The implications spread outward from physics in every direction. Dark matter makes up the scaffolding on which all visible matter assembled. It shaped the growth of galaxies from the earliest moments after the Big Bang. The first structures to form in the universe were dark matter halos, invisible gravitational wells into which ordinary gas fell and eventually formed the first stars and galaxies. Understanding dark matter's particle nature means understanding the foundation on which everything we see was built. For the Milky Way specifically, confirming a dark matter spike around Sagittarius A star would reveal something about the inner galaxy's history. Spikes only survive if the black hole grew slowly and steadily rather than through rapid mergers with other black holes. A violent merger history would disrupt and flatten the spike. Finding a sharp spike intact implies that Sagittarius A star grew primarily by consuming gas rather than by colliding with other black holes. The dark matter structure around the black hole is a record of how the black hole itself formed. The millisecond pulsar explanation, if confirmed instead, would be less groundbreaking for physics, but genuinely important for understanding the stellar populations of the Galactic Center. A large population of millisecond pulsars distributed through the inner galaxy would tell astronomers something about the rate and history of star formation and stellar evolution in the core over billions of years. It would help answer questions about how the dense stellar environment of the Galactic Center produces different types of stars and stellar remnants compared to the outer galaxy. Both answers advance science. One advances it modestly, the other shakes the foundations. The gamma-ray excess has sat in the data, unresolved, for over a decade. Every new analysis refines the picture slightly without decisively eliminating either explanation. The Galactic Center holds the answer. Extracting it is one of the central challenges of current astrophysics. Meanwhile, the physical processes at the center continue operating regardless of which explanation turns out to be correct. Gas flows inward. Stars form and explode. The black hole waits, and the midpoint cloud keeps feeding fresh material toward the most volatile region in the galaxy. The midpoint cloud is not just an interesting structure. It is an active participant in shaping the galactic center's future. The gas flowing through its internal dust lanes is heading somewhere specific. The central stellar bar sits at the end of that pipeline, and the bar feeds the innermost regions of the galactic center, including the zone immediately surrounding Sagittarius A star. Material delivered to the bar does not necessarily fall straight into the black hole. It enters a churning environment where it can spend millions of years cycling through star formation, stellar death, and recycling before any of it reaches the black hole's immediate accretion zone. But over long timescales, the statistical outcome is clear. Material that enters the galactic center region eventually gets consumed. The fraction that forms stars gets returned to the gas supply through stellar winds and supernova explosions. Some of that returned gas, enriched with heavy elements forged in the stellar cores, drifts inward and contributes to the next generation of star formation. Some falls further toward the black hole. The midpoint cloud represents a significant new input into this cycle. Astronomers estimated its mass based on the density measurements from the Green Bank telescope survey, and the number is substantial. Enough material to form thousands of stars. Enough gas to measurably alter the supply arriving at the central stellar bar over the next few million years. Whether that altered supply eventually triggers a new active phase in Sagittarius A star depends on how much of the material works its way inward past the star formation zone and reaches the black hole's immediate neighborhood. The path from the midpoint cloud to the black hole involves many steps, each with its own timescale and its own competing processes that can divert material away. But the direction of flow is inward. The pipeline is open, and the midpoint cloud has enough mass that even a small fraction of it reaching the black hole would represent a significant feeding event by current standards. Astronomers watching this play out over human timescales will see nothing happen. The relevant timescales are millions of years. No person alive today will witness the consequence of the midpoint cloud's current gas delivery. But the chain of causality is already running. The gas is moving. The cloud is collapsing in places. The stars forming inside it will live, die, and push material further inward through the cycle. The next chapter in the galactic center's violent history is already being written. It is just being written very slowly, and the new stars forming in the midpoint cloud will accelerate the writing. A star is born inside the midpoint cloud. This has already happened in at least several locations within the cloud, based on the maser signals the Green Bank telescope detected. Protostars are building mass right now, drawing in surrounding gas, heating their cocoons, and approaching the moment of nuclear ignition. Some will light up within the next few tens of thousands of years. On cosmic timescales, that is very soon. When those stars ignite, they will be massive. The environment of the midpoint cloud, saturated with gas under high pressure, favors the formation of stars many times heavier than the sun. A star 10 times the sun's mass burns roughly 10,000 times brighter and lives only a few million years. A star 20 times the sun's mass is even more extreme. Blindingly luminous, furiously hot, burning through its fuel in under 2 million years. During its short life, a massive star does enormous damage to its surroundings. The ultraviolet radiation it pours out ionizes the surrounding gas, creating a glowing bubble of hot plasma called an H2 region that can span dozens of light years. The stellar wind it blows, a constant outflow of charged particles moving at thousands of miles per second, carves a cavity in the surrounding cloud. Together, the radiation and wind inject energy into the midpoint cloud's gas that compresses nearby clumps and can trigger new rounds of collapse in adjacent regions. One massive star triggers more star formation nearby. Those stars, when they form, trigger more. The process cascades through the cloud, a chain reaction of stellar birth driven by the radiation and winds of the previous generation. Astronomers call this sequential star formation, and it is one of the mechanisms that allows a single molecular cloud to turn a significant fraction of its total gas into stars over a few million years. At the end of that short life, the massive star explodes in a supernova. The explosion, more energetic than the entire output of our sun over its 10 billion year lifetime. Compressed into seconds, blasts outward in all directions. The shockwave sweeps up surrounding gas, creates another hollow shell like the ones already mapped inside the midpoint cloud, and compresses more distant gas clumps into the next round of collapse. The supernova also enriches the surrounding gas with heavy elements synthesized inside the dying star's core. Carbon, oxygen, silicon, iron. Elements that did not exist in the original gas cloud get mixed back into the medium, changing its chemistry and its ability to cool rapidly under compression. Enriched gas cools more efficiently, which means it can collapse faster and produce stars more readily. Every explosion makes the next round of star formation slightly more efficient. The chain reaction strengthens as it goes. The material expelled by each supernova joins the flow already moving inward through the galactic center, enriched, energized, and carrying the kinetic energy of the blast. Layer after layer of this processed gas arrives at the central stellar bar, and eventually works toward the innermost regions. The machine runs on itself, and it is already running inside the midpoint cloud. The past behavior of Sagittarius A star was powerful enough to ionize a neighboring galaxy's gas trail. The question scientists sit with is whether something comparable will happen again, and what conditions would make it possible. The answer requires understanding what changed between the ancient active period and the current dormancy. Several million years ago, Sagittarius A star was consuming enough material to produce a sustained, brilliant flare. Today, it consumes almost nothing. Something shifted the gas supply available in its immediate vicinity. The most likely explanation involves the previous burst of activity itself. The flare and the associated energetic outflows probably heated and dispersed the gas in the innermost region, cutting off the supply that was feeding the black hole and sending it into its current quiet state. A feedback loop. The black hole became active, produced enormous energy, pushed the nearby gas away, starved its own fuel supply, and went quiet. This self-regulating behavior is observed in supermassive black holes in other galaxies, and it explains why even the most powerful active galactic nuclei eventually switch off. The gas does not stay away forever. Over millions to tens of millions of years, fresh gas flows inward along the same pathways that fed the previous active episode. The midpoint cloud's contribution adds to this inflow. Eventually, enough material accumulates in the innermost regions that the accretion rate rises again, the black hole activates, and the cycle begins once more. When that happens, the consequences for the inner galaxy are significant. A new active phase means new jets or outflow winds driving fresh energy into the galactic halo, new ionizing radiation flooding outward along the galactic poles, new pressure on the gas clouds surrounding the core, a new pulse of energy added to the already existing Fermi bubbles, potentially reinflating or reshaping them. Whether that activation looks exactly like the ancient flare is unknown. The current gas environment around the black hole differs from what existed several million years ago. The new generation of stars forming in the midpoint cloud will have altered the gas chemistry and distribution by the time their material reaches the core. The precise form of the next active episode depends on conditions that astronomers cannot fully predict across million-year timescales. What they can say is that the energy budget of the galactic center, the total amount of energy available from the black hole, the massive stars, the supernovae, and the particle acceleration, is vast enough that future events at the scale of the ancient flare are physically possible. The galactic center has done it before. The components that made it possible then are still present and still operating. For anything living in the outer galaxy, none of this poses a direct threat. The distance and timescales involved separate us completely from these processes in any practical sense. But the galaxy we live in is shaped by them. Every heavy element in your body was forged in a stellar core and scattered by an explosion. Some of that enrichment ultimately traces back to star formation cycles driven by the galactic center's violent history. The oxygen in your lungs, the iron in your blood, the carbon in every cell of your body carries the signature of processes running at the core for billions of years. The galactic center made parts of you. And it is not finished making the galaxy. The galactic center is not just a violent spectacle, it is a factory. Stars forming in the intense environment of the core burn faster and hotter than stars in the outer galaxy. Their compressed lifespans mean they move through the entire stellar life cycle from birth to explosion in a fraction of the time it takes quieter stars in regions like ours. Where a star like our Sun takes 10 billion years to exhaust its fuel, a massive star formed near the galactic center may complete the same journey in 2 million years. During those 2 million years, the star's core runs nuclear reactions at extreme temperatures and pressures. Hydrogen fuses into helium. Helium fuses into carbon. Carbon into oxygen, neon, silicon, and finally iron. Each fusion step produces energy and builds heavier elements from lighter ones. The star's core is an element factory, building the chemical inventory of the universe one nuclear reaction at a time. Iron is where the factory stops. Fusing iron absorbs energy rather than releasing it, which means that once an iron core builds up, the star's internal pressure drops and the core collapses in a fraction of a second. The resulting supernova explosion scatters everything the star built across surrounding space. Carbon, oxygen, nitrogen, silicon, all the elements heavier than hydrogen and helium that life depends on, get thrown outward in the explosion at tens of thousands of miles per second. In the galactic center, this process runs at an accelerated rate. More massive stars form per unit of gas than anywhere else in the galaxy. More massive stars means more supernovae per million years. More supernovae means more heavy elements scattered into the surrounding gas at a higher rate than anywhere in the outer disk. That chemically enriched gas does not stay in the core. The outflow is driven by stellar winds, supernova explosions, and the energy of the Fermi bubble inflation carry material outward from the galactic center into the broader galactic halo. Some of that material eventually falls back onto the galactic disk, mixing into the gas supply of the outer galaxy. Over billions of years, the heavy element content of the entire Milky Way has been building partly because the galactic center keeps generating and expelling enriched material. Our solar system formed 4.5 billion years ago from a cloud of gas in the outer galaxy. That gas was already enriched with heavy elements from billions of years of galactic chemical evolution. Some fraction of those heavy elements trace back to stars that lived and died near the galactic center. Their processed material transported outward over enormous timescales before eventually ending up in the nebula that collapsed to form our sun, our planets, and everything on them. Every atom heavier than helium in your body has a history. That history includes stellar interiors, supernova explosions, and the long journey through galactic space. Some of that journey started at the center of the Milky Way. The galactic center forged pieces of you before the Earth existed. The galactic center does not just affect the Milky Way through radiation and matter. It shapes the galaxy through invisible force. Magnetic fields thread through the entire galaxy, from the dense star-forming regions near the core to the thin, sparse gas of the outer spiral arms. These fields are not uniform. They follow the structure of the galaxy, winding through its arms, threading through molecular clouds, and concentrating in regions of intense activity. The galactic center is the most magnetically intense region in the Milky Way. Astronomers measure the magnetic field strength in different regions of the galaxy using a variety of techniques. Polarized light from dust grains aligned by magnetic fields traces field direction. The behavior of cosmic rays in the field encodes field strength. Radio emission from electrons spiraling along field lines reveals field topology. Combining these measurements paints a picture of the galactic magnetic field as a complex three-dimensional structure with the galactic center as its most concentrated and energetic region. The fields near the galactic center are roughly 1,000 times stronger than those in the outer disk where our solar system lives. At those field strengths, magnetic forces compete directly with gravity and gas pressure in determining how material moves through the core. Gas does not simply fall freely inward under gravity. It gets channeled along field lines, diverted sideways, and sometimes pushed outward by the energy stored in compressed magnetic fields. This channeling effect directly influences star formation. Dense filaments of gas inside clouds, like the midpoint cloud, align preferentially along or perpendicular to the local magnetic field direction, depending on how strong the field is relative to the gas pressure. The geometry of star formation in the galactic center reflects the geometry of the magnetic field threading through it. But the magnetic field's influence extends far beyond the star-forming regions. The Fermi bubbles are partly defined by magnetic fields. The sharp edges of the bubbles correspond to regions where the field lines have been swept up and compressed by the expanding bubble walls, creating a magnetic barrier that helps contain the high-energy particles inside the bubbles. Without those magnetic walls, the cosmic rays inside the Fermi bubbles would stream outward freely and the bubbles would dissolve. The galactic center generates and amplifies magnetic fields through the turbulent motion of conducting gas in the extreme environment of the core. Those fields then propagate outward, carried by the same outflows that drive the Fermi bubbles, and enrich the galactic halo with heavy elements. Over billions of years, the magnetic output of the galactic center has contributed to the large-scale magnetic structure of the entire Milky Way. The invisible skeleton of the galaxy, the field that aligns dust and channels cosmic rays and helps define the structure of spiral arms, has its roots partly in the processes we have been examining at the galactic core. Everything connects back to the center. The Milky Way's spiral arms are its most recognizable feature. Seen from outside, the galaxy would look like a pinwheel, 4 major arms of stars and gas curving outward from a central bar. Our solar system sits in a minor spur between 2 of those arms, a quiet suburban location in a galaxy that is anything but quiet at its heart. The arms themselves are regions of slightly higher gas and star density, places where the spiral density wave that organizes the galaxy's structure compresses material into bands that promote star formation. The spiral structure connects directly to the central bar. The bar, that elongated, rotating concentration of millions of stars at the core, drives gravitational resonances that reach outward into the galactic disk. Like the way a spoon stirring coffee creates a pattern that extends across the whole cup, the rotating bar at the center generates gravitational waves that organize material in the outer disk into the spiral pattern we see. Without the central bar, the Milky Way's spiral structure would degrade over time. Stars and gas would gradually smear into a uniform disk. The density waves that trigger star formation along the spiral arms and maintain the galaxy's organized appearance depend on the continuous gravitational input from the rotating bar at the center. The galactic center, therefore, does not just affect its immediate surroundings. Its structural influence organizes the entire galaxy on scales of hundreds of thousands of light years. The existence of stable spiral arms where star formation can proceed in an organized pattern across billions of years of galactic history traces back through gravitational dynamics to the central bar and the black hole anchoring it. Stars in the spiral arms form in giant molecular clouds compressed by the density wave as it sweeps through the disk. Planets form around those stars. Given the right conditions, chemistry progresses from simple molecules to complex organic compounds to biology. The entire chain that produced life on Earth required the organized structure of a spiral galaxy. And that structure depends on the dynamics of the galactic center. The galactic center shaped the architecture of the environment where life appeared. That connection is humbling. The violent, radiation-soaked, magnetically intense, particle-trapping, star-exploding engine at the core of the Milky Way is not separate from the peaceful outer galaxy where we live. It built the structure we live inside. It enriched the gas our solar system formed from. It maintains the gravitational organization that keeps star formation ordered and continuous across the galaxy's arms. The center and the edge are the same system. For all the progress made in the last decade, the galactic center is still largely unmapped. The midpoint cloud's discovery in 2025 made this point starkly. A 200 light-year-wide structure sitting in a region that astronomers had studied for decades went undetected until a team with the right instrument and the right survey strategy looked carefully. If something that large could hide for this long, the galactic center almost certainly contains other structures of comparable or larger scale that current surveys have not yet resolved. The transition zone between the ordered outer disk and the chaotic inner core, exactly the region where the midpoint cloud lives, is particularly poorly mapped. It is wide enough to contain multiple large structures, and the overlapping line-of-sight confusion that hid the midpoint cloud probably hides others. Future radio surveys with greater sensitivity and resolution will systematically map this zone and almost certainly turn up surprises. The dark matter distribution in the inner galaxy is another enormous unknown. Knowing whether a dark matter spike exists around Sagittarius A star, and if so, how concentrated and extended it is, requires measurements at sensitivities that current instruments cannot quite reach. The gamma-ray excess is a hint, but not a definitive map. Next-generation gamma-ray telescopes, particularly the Cherenkov telescope array currently under construction in Chile and the Canary Islands, may have sufficient sensitivity to distinguish between the dark matter annihilation and millisecond pulsar explanations definitively. The history of past Sagittarius A-star activity is also incompletely reconstructed. The ancient flare from several million years ago left evidence in the Magellanic Stream and in high-latitude ionized gas, but the precise timeline, the peak activity level, and the number of separate active episodes that may have occurred in the more distant past are not well constrained. Longer baseline surveys of more gas structures in the galactic halo may fill in that timeline over the coming decades. The galactic magnetic field in 3 dimensions remains poorly mapped. Current techniques give 2-dimensional projections that are difficult to interpret unambiguously in terms of the actual 3-dimensional field structure. New instruments designed specifically for magnetic field mapping, including space-based polarimetry missions being planned for the 2030s, aim to construct a full 3-dimensional model of the galactic field for the first time. Every gap in our knowledge of the galactic center represents a discovery waiting to happen. The history of the field over the past 2 decades has been one of constant surprise. Bubbles nobody predicted, clouds nobody noticed, signals nobody could explain, fossil records preserved in distant gas. Each surprise came from pointing a better instrument at a region people thought they already understood. The galactic center keeps surprising everyone who looks. Pull back. All the way back. Far enough that the Milky Way appears as a single flat disk of light, its spiral arms curling outward from a bright central concentration that glows across every wavelength of the electromagnetic spectrum. From this distance, the galactic center is just a point of light. But you know now what that point contains. A black hole with the mass of 4 million suns, sleeping at this moment but scarred by its own violent history. A central bar of millions of stars churning in chaotic orbits. A newly discovered 200 light-year wide cloud actively funneling gas toward the core through hidden internal rivers. Star nurseries flickering to life inside that cloud, announced by cosmic lighthouse signals from newly forming protostars. Ancient supernova shells carved into the surrounding gas by generations of stellar explosions. 2 enormous gamma ray bubbles stretching outward from the core, spanning a distance equal to the galaxy's full diameter, glowing with the trapped energy of a past event, powerful enough to reach a neighboring galaxy. A persistent gamma ray signal that either represents a known population of spinning stellar remnants or the first confirmed detection of dark matter particle annihilation. A particle trap running at energies 4 times higher than the most powerful machine humans have ever built. Magnetic fields 1,000 times stronger than anything in our neighborhood, threading through everything and organizing the forces that shape the galaxy's structure. An ancient blast from the sleeping black hole that ionized gas belonging to dwarf galaxies 160,000 light-years away. Evidence of that blast preserved as fossil ionization still slowly fading in the Magellanic Stream today. A self-regulating feedback loop in which activity feeds itself, disperses its own fuel supply, goes quiet, and then recharges over millions of years for the next episode. And running through all of it, the chain of causality connecting the center to everything else, the gravitational dynamics of the central bar organizing the spiral arms, the supernova-enriched outflows from the core seeding the outer galaxy with heavy elements over billions of years, the magnetic output of the central engine threading outward into the galactic structure, the chemical legacy of massive stars born and died at the core, ending up, billions of years later, in the bodies of living things on a small rocky planet, 26,000 light-years from the action. The galactic center is not a distant, separate phenomenon. It is the source, the origin of the galaxy's organization, the architect of its chemical history, the driver of its large-scale structure. Every spiral arm, every molecular cloud, every star system, every planet carries some record of what happened at the center. We are the outer edge of the most powerful engine in the Milky Way. We are made of material that passed through its processes. We look up at a sky that still glows, invisibly, from explosions our galaxy's heart produced millions of years before we existed. The center built the galaxy built us, and we are only now beginning to read what it wrote.